In this video, we're going to learn how to draw and evaluate plausible resonance structures. Resonance is generally a stabilizing phenomenon. One reason for this is that resonance allows electron density to be spread out over a larger volume. For example, let's look back at the resonance hybrid of the methyl acetate ion from a few videos back. Because of resonance, the negative charge can be delocalized over two atoms, carbon and oxygen, rather than just one or the other. Also, the lone pair from the red oxygen can be spread out across a larger area by resonating. So giving electrons more space to be away from one another is always a stabilizing effect since, of course, like charges repel one another. Also note that electrons can localize on more electronegative atoms via resonance. So in structure 4, the most electronegative atom has the most electron density around it, and that's a stabilizing effect as well. Now let's revisit HCN. So compare what's different between the two Lewis structures of HCN that we developed a few videos back. In the structure on the left, there's a carbon-nitrogen triple bond and one lone pair of electrons on nitrogen. In the structure on the right, there's a carbon-nitrogen double bond, but now we have two lone pairs on the nitrogen. So doesn't it kind of seem like maybe a pair of pi electrons moved from in between the carbon and nitrogen and then made their way over to the nitrogen in the second resonance structure? In reality, electrons are not jumping back and forth between atoms, and we really don't have two separate structures. Remember, the structure is really a hybrid of the two, and the electronic structure is somewhere in between what is depicted on the left and what is depicted on the right. However, it's really difficult to construct a mental picture of what's going on, so we have to make some simplifications. The convention in organic chemistry is to use a full-headed arrow to represent two electron movement. So we're going to show one set of the pi electrons move from in between the carbon and nitrogen over to the nitrogen atom. And then we're going to place a double-headed arrow between the two Lewis structures. And that's to indicate that they are contributors to a resonance hybrid. So it's important that we use what we know both about bond polarity and resonance to get a picture of how the electrons are actually distributed in a given molecule or given ion. So if we go back to HCN, we see that based on bond polarity, we predict that the nitrogen is going to have a little bit more electron density around it than the carbon. And we also get that same impression from the resonance structures. And so overall, it seems fair to say that the carbon is partially positive and the nitrogen is partially negative. And these partial charges are going to have direct consequences on the chemical behavior and the physical properties of HCN. There are a few basic rules about resonance that you need to keep in mind. Number one, only lone pair and pi electrons can participate in resonance. Sigma electrons do not resonate. So look again at methyl acetate. Notice that in every structure, the sigma electrons, which are in red, stay in the same place. Only the pi electrons or lone pairs differ in location. Number two, electrons resonate within a molecule because of overlap between non-bonding p orbitals and/or pi orbitals. In order for an atom to accept an electron pair during resonance, the atom must be sp2 or sp hybridized. Atoms with sp3 hybridization do not have the required p orbital. So once again, if you take methyl acetate, for example, the carbon on the far right in red never participates in the resonance. That carbon is sp3 hybridized and has a complete octet, so there's no room for another pair of electrons. But what about the yellow carbon on the far left or the green oxygen on the far right? It seems like both of those atoms are sp3 hybridized in 3 out of the 4 Lewis structures. That sort of leads to part B of this rule. If an atom seems to be flipping back and forth between two different hybridization schemes, the reality is that the hybridization is somewhere in between the two. So as long as the atom has some sp or sp2 character, it can participate in resonance. Number 3, only consider resonance structures that either increase the amount of space occupied by the electron density or that place more electron density closer to an electronegative atom. One mistake I very commonly see is for students to take a carbon-carbon double bond and just split it into a plus-minus species as shown here. Doing this does not accomplish spreading out electron density or moving any electrons towards an electronegative atom. So a word of caution is don't do this. Now the example I just gave is very different from this example. So suppose you have a molecule with two alternating double single bonds like this. You can resonate the pi electrons back and forth between these carbons, but that's because you're allowing the electrons to occupy space in the green box that was not occupied before. Let's practice drawing the appropriate resonance arrows on the methyl acetate structures to indicate electron movement. So to get from structure 1 to structure 2, I'm going to draw an arrow indicating movement of the one set of the pi electrons up toward the oxygen, which makes sense based on electronegativity that the electrons would want to go towards the oxygen. Then going from structure 2 to structure 3, I'm going to resonate in a lone pair off of the oxygen on the right down to in between the carbon and oxygen. That also makes sense because that carbon with an incomplete octet very much wants another pair of electrons. And then finally, to get from structure 3 to structure 4, I'm going to resonate in a lone pair off of the carbon on the left and then move these pi electrons back to the oxygen on the right so that now that oxygen will not have a positive charge, but all of the atoms will have complete octets. That last step actually accomplishes something else. Notice that the net result was getting a negative charge off of a carbon and also a positive charge off of an oxygen. And the only atom bearing a charge is the oxygen, and it's the most electronegative atom in the molecule, so that is a favorable electron movement going from 3 to 4. Now I want you to pause the video and practice drawing all of the reasonable resonance structures for this molecule and use the arrow notation to indicate how you get from one structure to the next. And then finally, draw the resonance hybrid of the molecule and identify the major and minor contributors to the resonance hybrid. Hopefully you were able to come up with these resonance structures. And here is the resonance hybrid and the ranking from major to minor contributor to the hybrid.